All right, welcome back. We're going to talk a little bit more about weather and climate. We've already discussed the structure of the atmosphere, and what we're looking at here is a diagram of the greenhouse effect. So the greenhouse effect is one of the things that's responsible for making life on Earth possible. Without the greenhouse gases, then the Earth would wind up being one giant ice ball with a greater buildup of greenhouse gases along the lines of Venus. You could actually have a situation where the area underneath the atmosphere gets way too hot and life cannot survive at all. So we need the buildup of these greenhouse gases, water vapor, carbon dioxide. We need those things to be able to have life survive and to be able to keep the temperatures underneath this blanket of greenhouse gases habitable. So basically what we have here is the sun's rays are striking Earth, like so. Some of that solar radiation can be reflected back off the top of the atmosphere. Some of that solar radiation can be reflected back off the tops of clouds. It can be reflected back off of ice caps. However, a lot of that radiation is intercepted and absorbed by the surface, by the greenhouse gases in the atmosphere itself. And a lot of this radiation then is re-radiated back to space. Well, the buildup of this greenhouse gas blanket can actually trap some of that re-radiating heat underneath it. It also allows some to get through, but some does get trapped. So the fact that this energy is getting trapped is going to cause temperatures underneath the blanket to rise. In a nutshell, that's the greenhouse effect. We began discussing meteorology. We began discussing things that we talked about low pressure. We talked about low pressure equaling rising air. And what I want to discuss with you is a couple of things that are actually going to cause air to rise. Things that cause air to rise. One is orographic lifting, or basically air goes over top of a mountain. Air goes up over top of the mountain. As it increases in its altitude, it's going to cool. That water vapor that's in there condenses into these clouds, and here you have precipitation resulting. Other things that cause air to rise. Convection, localized convection. We see this during the summertime a lot. You've got the surface heating up because of sun. The air at the surface becomes warmer. So let's say it was originally occupying this much space. As it heats up, it's actually going to expand, all right, and occupy this much space, and it becomes less dense. As it expands and becomes less dense, it wants to rise. Okay. Another reason why air rises are frontal boundaries. So cold fronts, warm fronts. A cold front is designated by blue lines and blue teeth on a weather map. A warm front is designated by a red line with these nice red semicircles on them. Okay, here's what happens with a cold front and a warm front. So what we have here is we have the surface, and let's say we have some warm air in place. Here is the frontal boundary. These teeth actually point in the direction that the air mass is moving. So what we've got back behind this front is we have this big mass of cold air. And that cold air is moving in this direction. We talked about cold air being denser than warm air. So this cold air will force this warm air upward. And as it forces that warm air upward, it's going to cause clouds to form. And what you'll see along the frontal boundary is you'll see some intense storms right here along the frontal boundary where this uplift is taking place. With a warm front, however, what you have is here's the surface, and what you've got is you have cold air already in place. Here's the front. Again, this warm air is moving in this direction. And what we know is that warm air is less dense than cold air, so that warm air is actually going to slide up the surface of this cold air. It's going to wind up creating stratus clouds all along this whole area, and you're going to have widespread showers in front of that frontal boundary, simply because that warm air is going to be climbing upward. So you're going to have showers spread over this whole area. And that's basically what fronts are. And as you can see in both of these cases, the warm air is forced to rise. So we just talked about fronts. Here's the diagram for fronts again. We'll go to the next one here, and this is surface convergence. And we talked a little bit about this today, where we talked about warm air converging at the surface. Okay, think about this as being, again, as you see on the diagram here, a low pressure center. So there's a big red L here. So you've got air coming in this direction, air coming in this direction. When it meets, it goes up. And when it goes up, it's going to create these clouds, and you're going to wind up having precipitation. So those are the four main things that are going to cause air to rise. You're going to have surface convergence, you're going to have orographic lifting, or going over a mountain. You're going to have convection, and you're also going to have frontal boundaries that are going to cause that air to rise. All right, so let's talk about climate. The Earth's atmosphere does have physical features that change day to day, as well as patterns that are consistent over a space of many years. The day-to-day properties like wind speed, wind direction, temperature, amount of sunlight, pressure, humidity, all of that stuff is weather. The patterns that are constant over many years, 30 years or more, so 30 plus years, there we're dealing with climate. The two most important factors in describing climate are average temperature and average precipitation amounts. The map that you're looking at shows different types of climates: tropical, dry, moderate, continental, polar. Okay? All of these things are dependent upon average temperature and average precipitation amounts. The weather and climate of any of these given areas is the result of the sun unequally warming the Earth and the gases above it, as well as the rotation of the Earth. We'll get back to these climate types, biomes within these climate types at a later date, especially when we start talking about soils as well. So here we're actually going to talk a little bit about circulation in the atmosphere. Okay? The motion of air around the globe takes place because of solar heating. It takes place because of the rotation of the Earth. And that's where we talk about Coriolis. I gave the example of the spinning playground wheel of death. And because of the physical properties of land and water. And for the most part, air as well. These things right here are the reason that we've got air circulation. Okay? So, taking a look back at this map. So, more of the sun's rays are going to strike the Earth at the equator, okay, than it will at the poles. And that's because the Earth is tilted. Most of the sun's rays are going to strike directly, all the sun's rays are going to strike directly at 90 degrees overhead in this area, between 23.5 degrees north and 23.5 degrees south. The reason it's 23.5 degrees is because that's the tilt of the Earth's axis at 23.5 degrees. The tilt of that axis points regions toward or away from the sun. When a hemisphere is pointed towards the sun, that area is going to receive more direct sunlight. than it will when it's pointed away. This is why we have seasons. The Earth's surface at the equator is moving faster than it is at the poles. This changes the motion of air into major prevailing winds, which are belts of air that distribute heat and moisture unevenly. Winds moving north from the equator in the northern hemisphere are deflected to the right, and winds moving south from the equator in the southern hemisphere are deflected to the left. This is the Coriolis effect. We talked about that before. So basically what we need to understand is that solar energy warms the Earth's surface. The heat is transferred to the atmosphere by radiation heating. The warmed gases, they expand, they become less dense, they rise, creating vertical currents called convection currents. The warm currents also hold a lot of moisture compared to the surrounding air. As these huge masses of warm, moist air rise, cool air flows along Earth's surface into the area where the warm air was located. The flowing air, or this horizontal airflow, is one way that surface winds are created. So what we see here is we see a convection cell, and we see this radiator. We just talked about radiation heat. So the air right here is warmed, it expands, becomes less dense, and it rises. Okay? This cooler air over here is going to move horizontally to take its place. All the while, this air is going to get closer to the radiator, so it's going to warm, and it's going to rise again. This air right here is actually going to wind up flowing in this direction. And again, we talk about surface and pressure, surface pressure and pressure aloft. Air rising in location A has a surface low. If it moves from here up, this location B is going to have high pressure aloft. Over here in location C, we've got a surface high pressure because we have air descending. At location D, we've got a pressure low aloft. So again, winds blow from high to low. They blow from high to low. And that creates this big convection cell. So as warm, moist air rises into the cooler atmosphere, it cools to what's known as the dew point. And the dew point is the temperature at which water will condense. That condensation in turn creates clouds. If condensation continues, the drops get bigger. It can no longer be held up by the convection in the Earth's atmosphere, and they fall as precipitation, which in the northern hemisphere, all precipitation starts as frozen precipitation high up in the sky. The cold, dry air is now denser than the surrounding air. The air mass then sinks to the Earth's surface, where it's warmed again and can gather more moisture, which is what we're seeing in this part right here, thus starting this convection cell or this convection current again. I'm going to stop here because I'm approaching 14 minutes. I will pick up on the next slide in my next video. Thanks.